Okay. I will be your professor for today. Okay. You should take out your periodic table, because I'm gonna refer to it a whole bunch. So you should pull it up. You should pause for a second and pull it up. Okay. So first, I'll tell you what the Lewis structure is, basically. It's basically just a structure of electrons, just showing the electronic structure and how they connect with each other when you form compounds. But we'll start off slow with phosphorus. So that's in group 3, and it's number 15. It's gonna be P right here. All right. So I don't know if you could see, but on your periodic table, it's gonna be in row 5. It's gonna say 15, so row 5. That means it has 5 electrons, right? So then we fill up one orbital at a time. So it goes 1, 2, 3, 4. And then, since it has 5, now that these are all filled, we start on the next one. And then, I'll make that a little bigger so you can see. Then that's phosphorus. That's a Lewis structure for phosphorus. All right. Very cool. So the next one we're gonna do. We'll do another one of those, and then we'll make a little formula. But yeah, electron each. It fills up all of them, all 4, and then it goes back around again. And that is phosphorus. So let's say we were doing fluorine, right? F. Beep, beep. So, what row is it in? Pause and check. Okay? So that says it's row 7. And then we do 1, 2, 3, 4, 5, 6. All right? And that's for fluorine. Simple. The electrons just go around it in pairs of 4. So 1, 2, 3, 4, 5, 6, 7, 8. Then you're done. So this is Lewis structure for fluorine. All right. Now, when it comes to making structures, right? When it's like this, O, H, what we're gonna see on the test, right? We need to know which one of these elements is our something called a central. Which one is our middle element, right? And we know that by saying, okay, which one is the least electronegative? Which I'm gonna explain right now, okay? So imagine this is the periodic table, right? So we have fluorine over here, let's say hydrogen up here, and like lithium down there. You get the picture, right? So you get more electronegative as you go this way, right? You get least electronegative going that way. And something called a atomic radius, that increases as you go that way. So as you go down and as you go left. Okay? Now there's also something called ionization, right? So ionization levels also go along with the electronegativity. So just for labeling, this is atomic, and I'm gonna explain why in a second. Atomic radius, electronegativity, and ionization. Okay, so I know you're gonna ask me why. So the atomic radius goes down. Atomic radius increases because if you think about an element, right? Think of an element like a closet, right? And now, as you get more towards fluorine, there's more electrons going into this closet, right? So they're getting filled up. So there's less room in it, which means the radius is smaller, right? So as you see on your periodic table, what is this over here? 1, 2, 3, 4, 5. It's getting more are going toward the 6, 6, 7, 8. More electrons are fitting into this element. So the atomic radius is smaller. But as you go down and left, less electrons means more room, which means the atomic radius increases. So think of it as like space in a closet. The more electrons means the more clothes you're stuffing into the closet, which means there's no space in there. But the less clothes you have in the closet, the less electrons you have, means the atomic radius goes down, right? Now, ionization, right? So this is talking about electrons again. And basically ionization, all it is how closely these electrons want to be to each other, right? So think of electrons like magnets. They have a force that pulls them together, right? They have a force that pulls them together. And the more magnets that you put on each other, the harder it is going to be to take away from them because there's just so many magnets, they want to stay together, right? So, which is why the ionization level goes up. One magnet by itself, okay, that's nothing. 2 of them, now they're holding a little bit together. 3 electrons, it's getting more compounded, they're holding on to each other more. And as you increase, the ionization levels goes up, which means it takes more energy to take those electrons apart because there's more of them together. Got it. And electronegativity, it follows the same line of ionization. So a good rule of thumb is these are proportional. Electronegativity and ionization are proportional, and atomic radius is not. So there you go. I'm going to take this down in a second. Okay. Uh-oh. Let's back up. Scout. Let me make sure that you can still see. Cool. Okay. So we are going to be making the Lewis structure. We'll start off with O first before we add the H, okay? So this is just O, oxygen, right? So you tell me, check your periodic table, let me know which row it's in, right? And as you see, you check it, you're gonna find it, it's gonna be like, okay, it's in 6. So this has 6 electrons. Okay. Now if we have 6 electrons, let's draw our Lewis structure. 1, 2, 3, 4, 5, 6, 6. It goes all around once, and then it fills it up. So fill up everything first, then start on the next one, okay? And that is oxygen, right? Okay. Now, for drawing a Lewis structure, you would need an H minus. Now we're gonna draw this one, okay? First things first, we are going to add up the electrons. That gives us the ability to make the structures in the first place, okay? So, how much does oxygen have? 6. 6 plus hydrogen. How many does hydrogen have? 1. Plus the 1 minus right there, that's another electron. So it's 6 plus 1 plus 1, which equals 2, 8. So we have 8 electrons, okay? Now, I told you before, how we start off our Lewis structure is the less electronegative, which means going this way, or down, down, or left, right? But the thing with hydrogen is, it will never start its own up. Never, never. If you see hydrogen, it's not starting the Lewis structure. What's starting the Lewis structure is oxygen. And we'll go upon that more, trying to find out which one is which, because that could be tough too. But it's never hydrogen. Rule, never hydrogen. So it's oxygen, right? And we connect them with something called bonds, okay? Now each of these bonds, right, are worth 2 electrons. So that's 2 electrons. Worth 2 electrons, okay? So now, these are both good. They're connected with 1 bond worth 2 electrons. So we do minus 2. That's 6 electrons, right? Then, what we do with these 6 electrons is, we fill up something called an octet. Okay, and I'm gonna go into an octet. So what an octet is, there needs to be 8 total. 8 total electrons, because, how do I want to explain this? Okay. So if you look at your periodic table, right, you see your noble gases all the way on the right in row 18. In row 18. At row 18, right? So 8 electrons all of these elements have in the noble gases. So the goal is to make these elements hit those noble gases, right? Get the enough electrons to get into those noble gases. So we see H, right? These 2 electrons, H becomes helium. It becomes the noble gas in a sense. It has 2 electrons, which means it's done. Boom, H is done, right? But now for oxygen, it has 2 electrons, but it's asking for 8 in this row. So we're gonna give it a little bit more. And it's gonna look just like this. It has 6. We have 6 more electrons. It already has 2. So we go 1, 2, 3, 4. Sorry. It goes 1, 2, 3, 4, 5, 6. And now it completed its octet rule. The octet rule, these got 8 electrons. The hydrogen became helium because helium has 2 electrons. Now we're done. Barbecue chicken. We're good. That's it. And we're gonna do another one, okay? We have a whole bunch. But this is how this would look. The 6 go here. This becomes 8 electrons. It's all good. Helium gets the 2. Hydrogen gets the 2 electrons. It becomes a noble gas, becomes helium. Now that's good. Okay? And we will continue. Give me 1 second. Okay, what is that? O2. O2 minus. Okay. People watching.
Can you open the door?
Yeah. Thank you, Matt, please. Can you open the door, please? Okay.
Is this chemistry?
Yeah.
Oh. Is why you're hanging around here?
Yeah, you're all good, bro.
Alright.
Oh.
Thanks.
Yeah, bro. No problem. continue making our Lewis structures. We'll do another one. This is O2, 2 minus. Okay. O2, 2 minus. Yeah. So O, it's in 6, right? It's 16, but really it's 6. So it has 6 electrons available. So then we do 6. And there's 2 oxygens, so 6 plus 6, plus the 2 minus electrons, so we add 2. And that equals 12 plus 2, which is 14. So we have 14 of available electrons. First thing we do is connect them. Cool. And that is minus 2. And that gives us 12. And then all we do is follow the octet rule and fill it up. And it goes like this. 1, we have 12, so I'm gonna use 6 on this side, 6 on this side. And this goes 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we're done. That's it for O2, 2 minus. That's how we do it. We just add it. 1, 6, 2, 6, because there's 2 of them, plus the 2 minus electrons. That gives us 14 available electrons. We connect them. First thing you do, that gives us 1 bond. And 1 bond is worth 2 electrons. So we do 14, which we got from this, minus the bond, which gives us 12 available electrons. And then we can fill up its octet with 6 on each side. 1, 2, 3, 4, 5, 6 on this side. 1, 2, 3, 4, 5, 6. And now we're good. And that's how you do it. Keep in mind the electronegativity rule that we were using to see which one we use. Okay, they're the same. Oh, sorry. And for stuff like this, they're going to be names to describe what type of bonds it is. This would be a pure covalent bond. Give me 1 second. Yeah. This is a pure covalent bond. Basically, the pure just means they're the same element. And the bond is that they're equally sharing electrons because they're the same element. That's it. So, P to P, T to T. Pure covalent bonds. So the same thing, they are purely sharing electrons, basically. That's how I'd like to think about it. All right? They're the same element. Now we'll do polar covalent bonds. Polar covalent bonds. Okay. Polar covalent bonds. This is just unequal sharing of electrons. So let me see which one it's in. BR and P. Okay. BR and P. Okay. P. BR. So P. BR. Right? This is a polar covalent. Polar meaning they're not sharing equally. So if you see, phosphorus has 5 electrons, right? Phosphorus has 5 electrons, and Br, bromine, has 7 electrons, and these are not equal. So they are polar covalent bonds. Anything, as long as they're not sharing equally. So we could do C with F. It's polar covalent bonds, they're not sharing equally. C is 4, F is 7, polar covalent bonds, not sharing equally, they're different. Oh, okay. Oh. Last one is, we know this one, ionic. These are always fun. Metal and non-metal. So that is, what did it use? Ca and I? Ca and I. I is 7. Ca is 2. And they're also metal and non-metals. So ionic. You know ionic. Okay. Now I think we could draw some more Lewis structures. Now that we know. Boom, boom. Okay. Okay. CCl4. So we're gonna do C. So we're gonna do CCl4. While I'm putting my chapstick on, find their electrons. Find how many electrons there are. Pause the video. Find how much. Okay. So we see chlorine is in 17, but 7. So that's 7 times, there's 4 of them, so 7 times 4, plus, let's see where C is at. C is in 14, so 4 electrons plus 4, and now we're good to go. So that's really just 7 times, sorry, 8 times 4, but it don't matter. So this is 28 plus 4, which gives us 32 electrons, and let's do it. So, which one would be the central? Which one would be the central atom that we are gonna build upon? Another rule of thumb is, which one's like, in this case, there's 1 and 4, so it's gonna be C surrounded by the 4 chlorines, but it's the most electronegative, so we're gonna go with that one. Chlorine is closer to fluorine and closer, how we were talking about the box, is closer to this side. Chlorine's on this side, while carbon is all the way over here. Right? So this one's obviously closer. That one's more electronegative. And then, so we put C in the middle, then we attach it. Chlorine, 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 chlorine. Cool. Okay. Now, this is the first thing. This is a skeletal structure. First thing we do, we write that out. Boom. Now they're all connected, and let's find out how many electrons we use to make this initial structure. So this is 2, this is 4, this is 6, and this is 8 electrons. Each bond is 2. So we do 2, 4, 6, 8 minus 8. Then this gives us 24. Now, carbon's octet rule is completed. It has 8 electrons on every side. So 2, 4, 6, 8. Carbon's good. Carbon's good. But we have 24 extra electrons, and all of these aren't completed, right? So we're gonna put the six each, right? And we're gonna see how it adds completely up to 24. So 1 over here, 2, 3, 4, 5, 6. Boom. That gives us 18. Now we're gonna just keep moving on. 1, 2, 3, 4, 5, 6. That octet is complete because it has hit 8 electrons, noble. Alright? Minus 6. Yes, I just added. Now we're gonna do this one. 1, 2, 3, 4, 5, 6. Minus 6. Now we have 6 left. You know where it goes. 1, 2, 3, 4, 5, 6. Cool. And now we can also say what type of bond do we have. We can say this is a covalent bond, carbon and chlorine. We can say it's covalent because they're not sharing equally. All right. And this would be our structure. So take a look at this, absorb it. I'll go through it again. So we have our central atom. Not only is there just one of them, but also it's the least electronegative. So that goes in the middle. And then we just attach it. Boom, 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 boom. Right? Now this is 2, 4, 6, 8. Minus the 32 electrons we started with. This is 7. There's 7 of these, right? Sorry. Chlorine has 7 electrons, and there's 4 of them, so that's 7 times 4 is 28, plus another 4, which gives us 32 electrons, right? Now that we've connected them, forget that these little dots are there. We do minus 8, and that gives us 2, 4, 6, 8 electrons, so we minus that, and now we have 24. Carbon is good because it has 8 electrons, completing its octet rule. 2 here, 2 here, 2 here, 2 here, done, right? Now, we can see this, and we have 24 available electrons, right? Now let's start putting them in. We put them here, done. Octet rule for this chlorine is complete. Put it here, boom, 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 boom. Another 6 gone, octet rule for this is complete. Another 12, boop, octet rule for that is complete. And the last one, octet rule for that is complete. So, for row, what was that? I always get that. So group 1 and 2, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, those can only have 8 electrons in its octet. It's limited. But you're gonna see later on that group 3 can overload its octet. It doesn't have that rule. But for boron, carbon, nitrogen, oxygen, fluorine, neon, those in group 2, they follow the octet rule, only having 8 electrons in its octet. That's their rule. All right. Okay. Cool. All right. And that's it. What you should do is, you should just practice just making an easy Lewis structure on ChatGPT. Pause it, make one, because we're gonna expand upon this in a second. So do a practice one. Do like 2 of these. I'm watching. Do 2 practice Lewis structures, right? Count the electrons, connect the bonds, see which one goes in the middle, the least electronegative, and fill in the octet rules, and then you're good. So I'm gonna take this down. Okay, what's this next one? I already did out too.
All right, Clo 3.
Okay. Was that Clo 3 2? Clo 3. Forgot the charge.
Minus.
Okay. Clo 3 minus. Let's do it. Okay. Okay, so Cl has 7 electrons. That's 7 plus the 1, that's minus, plus the 1, so that's 8, plus 3 O's, which means that's 3 times 6. So this is basically just 8 plus 18, which gives us 24 electrons for this compound. Okay? Now, we're gonna fill it up. Now I know you're probably thinking chlorine is more electronegative, right? But there's 3 of these. So all we're gonna do, we're still gonna focus on filling up the octet rule, but we're just gonna connect it to the oxygens. Right? This is how we could do it, and now we're good. And they're all connected, they're all touching, and now we're just gonna fill up their octet rule. All right? So it's gonna be 20, so now we have 24, that's 8 plus 18. No, that's 26. That's 26. Okay. Yeah, that's 26. Okay, so now 2, 4, 6 minus 6. Oh. Minus 6. Now we got 20. Okay, now we fill it up like the last one. So now we do 2, no, 1, 1, 2, 3, 4, 5, 6, filled. Minus 6 is 14. 1, 2, 3, 4, 5, 6, minus 6. That's 14 minus 16. 14 minus 6. 8. I need a lifeline. Okay. And then we just continue on filling up the octets. 1, 1, 2, 3, 4, 5, 6, minus 6. That gives us 2 electrons. And where do these 2 electrons go? Right into chlorine to fill up its octet rule. And that's it. And we can always check by making sure that it at least it follows the original octet rule, which is just 8 electrons. Now it could break it because chlorine is in group 3, but it follows the octet rule. As long as it follows it, we're good. Okay? So this is 2, 4, 6, 8. So if we're doing a checklist, chlorine is good. 8 electrons. It's chilling. Now let's see these. Each oxygen has 1 bond, which is 2 electrons, with 3 pairs of lone electrons, which is what they call this, so 3 pairs of 2, which is 6, and then this has 8 electrons. This one also has 1 bond, plus 3 lone pairs. So if they say 3 lone pairs, that's what they mean. That's the wording they use it. 3 lone pairs of electrons, and that's for O. Now for this, another bond, 3 lone pairs of electrons, and now all 3 octets are good. So take a second, check this out. Let's soak it in for a second. Okay. Now, this is a minus charge on this compound, right? I'm gonna show you where it comes from. So there's something called a formal charge with Lewis structures, right? Basically, formal charges, they help us determine what's the best and most stable Lewis structure. But for right now, don't worry about stable. We're just gonna focus on the actual formal charges, okay? So then O, we're gonna check its formal charge. And we do that by seeing what it has, and then I'm gonna show you what the formula is, okay? So it's how many electrons this element has, so I'm talking about O, this one in particular, right? It has 6 electrons, minus the bond, minus 1/2 the electrons of its bond. So this has 1 bond, right? 1 bond. And 1 bond is equal to 2 electrons. So half that is 1 electron. Minus 1. Minus how many lone pairs of electrons are out here. Not how many lone pairs, how many electrons in total. So 3 lone pairs means 6 electrons. So minus 6 is equal to -1. I'm gonna do that again. That was for this one. Now we're gonna do this one. They're all the same, but it matters. You gotta, because some bonds will be different. Some will have something called a double bond. Some will have single bonds. You need to make sure which one you're talking about. Okay. So now we're gonna do this one. Okay. What does this have? What's the formula? I'll write it down.
See if you can see that. Okay. Yeah, you can.
Okay. So what this means is the initial electrons minus the electrons of the bond, but 1/2. So if they have 2 bonds, that's 4, so that's gonna just be minus 2 electrons. But in this case, we have 1 bond, right? So it's minus 1, then minus the 6 electrons, or the free electrons, the dots around it, right? So we have the initial electrons, which is 6 for oxygen, minus 1/2 of the bond, so that's 1 bond with 2 electrons, half that, 1 electron, so minus 1 electron, minus how many electrons are out right here. We have 1, 2, 3, 4, 5, 6, minus 6, which gives this a formal charge of -1, and we can just write that by putting a fat minus right there. And that's the formal charge for that oxygen. So let's check this one. This one up here, that is, yeah, you see it. So let's start. First thing we're gonna write is how many electrons the element has, which is 6, minus 1/2 the electrons of its bonds, which is, it has 1 bond, 1/2 of 2, it's 1 electron. Minus 1 electron, minus how many dots it has, or lone pairs, but lone pairs are 2, so if it has 3 lone pairs, then times 2, so that's 6 electrons that are free. Minus 6 electrons is equal to -1, and this one also gets a negative. Same thing goes for this one. I'm running out of space. They're all the same. Same thing goes for that one, so this one also gets a minus charge. Okay. Now for chlorine, it's different. Let's check its charge. So, first off, that's 3 minus charges. 3 minus charges, okay? Because -1, -1, -1, we're all the same. So the oxygens in this one have a -1 charge, so there's 3 of them, 3 times 1 is equals 1. So negative minus 3, 3 minus charges. Okay? So now we're going to check the formal charge of chlorine, okay? So chlorine, there's 7 of them, right? So because there's 7, we start off with 7, not 6. Start off with 7. Chlorine has 7. 7 electrons. Okay. How many bonds does it have? This is not a bond. 1, 2, 3. 6 electrons split in half, which is just 3 bonds. A trick you could do is, whenever you get to minusing the bonds, just count how many bonds. You don't have to do 1/2 because you can just count it. But you know they're worth 2. So 3 bonds minus 3, but if you want to understand where that comes from, it's the bonds, the amount of electrons of the bonds, 1/2 of that. So this is 2, 4, 6. Split it, that's 3. So minus 3 electrons, right? Then we do the free electrons, right? And then that gives us the 2 right here. So this is 1, 2. Then we just minus 2. And it'll follow that form. It'll follow that formula every single time for formal charges. So this is 7 minus 3 minus 2. That's fine. That equals to a plus 2. So if you're asking, how does this chlorine trioxide have a charge of minus 3? We do this. It has 3 minus charges plus the 2 that we got from chlorine is equal to a minus charge. And then that gives us the charge of the whole structure. Okay? Alright. And yeah. That's formal charges. ChatGPT a question, do the formal charges, do like 2 questions of doing formal charges, just finding it out, okay? And you can watch this video to check. To play back.
Let me see if the video's still good. Yeah. Okay.
Cool. And this covers like everything that you've been missing. That's why it's long, so I'm trying to fit like 4 lectures in one for you. Okay.
The next thing we're gonna do is give me 1 second. I'm still here. Just give it 1 second. Okay. Nitrate. Okay. Minus NO2 minus. Okay.
We're going to talk about something called resonance bond. I don't know how to spell resonance, but you do. I'm not the best speller. But resonance, we're gonna go over it. But first things first, we're gonna solve this like any other one. So 2 O's, which is 2 times 6, plus N, which is 7, plus 1, that's 8. So this is really just 12 plus 8, which gives us 20 electrons. Okay, and then which one's in the middle? Which one's the least electronegative? N. Also, there's one of it, 2 of the other ones. You know what I mean? Keep it simple. So, N is the electronegative, so we're gonna do N is in the middle to O, and that was -4 electrons, which gives 16. And now we're gonna run into a problem, but I'm gonna let us run into it, okay? So we're gonna do 2. So we're gonna fill it up how we tried to before, okay? So we're gonna do 2, 3, 4, 5, 6. Bow. -6, which gives us, wait, 2 times 6. I just wanna make sure I did it. No, N is 5, sorry, N is 5. My bad. N is 5. So that is 6 times 2 plus 5 plus 1. So that's 6 times 2 plus 6, which is 18. Cool. 18 electrons we're starting out with. Minus the 4, because 1, 2 electrons each for these bonds. Minus 4, that gives us 14. There we go. And now we're going to try to fill it up. Fill these octets, right? So this is 1, 2, 3, 4, 5, 6. Always try to fill the oxygen octets up first. Just to roll it down. So we're going to fill the outer ones up. So that's 6. 1, 2, 3, 4, 5, 6. Minus 6. And that gives us 8 left. Now we're going to fill this up. 1, 2, 3, 4, 5. Why can't I count? Oh, I can. 1, 2, 3, 4, 5, 6. Okay. Minus 6. That gives us 2. And the last 2 go there. What is our problem? N is not completing its octet. There's not 8 electrons with N. There's only 6. 2, 4, 6. And that is not good. So there's a way to fix this. So we're going to make a new type of bond that you haven't seen yet. And all we're going to do is make something called a double bond. All right. So we have these right here, right? And we're going to recreate it so that one of these shares its 2 electrons and becomes a double. And I'm going to do it for you, okay? So this is O over here, and O. This is our second one. This was the skeletal. This is going to be our correct one.
I just want to make sure.
Okay. Oh, let me make sure that you can see it.
Oh, you can.
Good. Okay. All right. So then what we do is we have our electrons, and we know that there's not enough electrons in order to fill this octet, right? So what we could do is, I'll take from this side, for example. You see these 2 electrons right here? They're not gone. I'm just gonna make it a double. So this still has its 2 electrons, but it's just we're sharing them now because there's not enough to go around. So we're gonna share, and now we have a double bond. So now this has 4 electrons, which means this has 2, 4, 6, 8 2, for 6 electrons right here, okay? So now, we do it again. So now we have 18 at the start, minus the 6 electrons, and that gives us 12. 12 electrons left because 2, 4, 6. All I did just now was move these 2 electrons and become a double bond between N and O. So now, O has 4 electrons from the start. 2 times 2 is 4. This one has 4. This one has 6 because it has 2 over here, 4 over here. This has 6. And this one still has 2, okay? Double bonds mean these two are this one was increased. This one still has the same amount, they're just sharing now, okay? And then you just fill up the bonds again. And we'll do another one after this so it just really clicks. So 18 minus 6 gives us 12 electrons left, minus 6 because each of these bonds are 2. And then you just fill it up. 1, 2, 3, 4, minus 4. That gives us 8. This one's good. And I did it like this because imagine this electron, these 2, right there. So that's why I wrote it like this. I didn't go around how I had been doing before. Okay? Now we have 8 electrons left. Let's do this one. This one still needs 6, so we're gonna give it 6. 1, 2, 3, 4, 5, 6. Bow. Minus 6. That gives us 2 electrons left. And where does those 2 electrons go? Right here. Okay? And now, let's check it again. Same amount of electrons, we just use them differently. Now let's see if it completes the octet rule. 2, 4, 6, 8. That's good. 2, 4, 6, 8. That's good. This didn't change, but we'll check it again. 2, 4, 6, 8 electrons. That's good. Perfect. Now take a look at this, because I'm gonna erase everything except this. So I'm gonna give you a second. Take a look at that. Okay. Now, if you remember, we were talking about resonance structures at the start of this question. Now, this is something called a resonance structure, and let me tell you why. So a resonance structure is just a structure that can be, you could change the format, but it's still the same thing. But you can't change like the amount of electrons or the configuration. So I'm gonna show you that. So we see how we have the double bonds over here, right? Where I'm gonna draw another resonance structure, same one, right? And so we can't change this configuration. This has to happen. Because this is the central, so it needs to have 1 to each. We can't change that. But instead of having the double on the right side, we can put the double on this side and just follow the same rule. It still has the same amount of electrons. All we did was move it to the left side. And this still has 8 electrons. This still has 8. This still has 8. This still has 8. So it still completes the octet rule. It's just, it's a resonance structure because it could go on both sides, right? Now, would this be a resonance structure? I feel like an itch on my ear, I don't know. Would this be a resonance structure? No. The answer is no, because we switched the structure of it. It's supposed to have 1 to N since it's the central each. So O to N, O to N. But because it doesn't, we know this is not a resonance structure of this compound. And while we're here, we can do the formal charges just while we're here. So why don't you do the formal charges? Remember, amount of electrons minus how many bonds it has, and then minus, what am I thinking of? Minus the lone pairs of electrons. And then that's it. So, you do it, and I'm gonna do it. Pause it, I'm gonna do it now. So this is gonna be, for this oxygen right here, we are going to do 6 minus we're going to do 6 minus 2 minus the 4 electrons here, and that's going to give us 0 for this one. So 2, that gives us 4. And then these have 2 bonds, minus 2. And 6 is the original. So that gives us a 0 charge for that one. Okay? And then we're going to check N. So let's see N. N is 5, right? N is 5. Meek. 5 for N. How many bonds does it have? 3. Minus 3. 1, 2, 3 bonds. Minus lone pairs, which is 2. Which is just 1, 2 electrons, right? This is not an electron. This is a mistake. Just these 2. 1, 2. Those are the electrons. And its octet rule is full. So then minus 2, and that equals to 0. Now we're not done, because obviously this has a minus charge. Where does that minus charge come from? The other oxygen, which is this one right here. And now we're going to do that one. So I'll do it right here, which I was looking at. This oxygen. What do we start with for oxygen? Always 6. Minus. How many bonds does it have? 1. Minus 1, or 2 electrons. And 1/2 of that gives us 1. 1/2 of 2. But I just like doing it like that because it's so simple. Minus how many bonds it has. You don't have to divide, it's the same thing. Minus 1 bond. And how many electrons are free over here? There's 6, so 3 lone pairs minus 6 electrons. And that gives us a charge of -1. So we have 0 for the oxygen, 0 for the nitrogen, and this oxygen has a -1 charge. And we know we did this correct because 0 plus 0 minus 1. That gives us a -1 charge for the entire thing. But the main takeaway from this was, this is a resonance structure. We can flip it, but we cannot change how it's structured. Okay? So we could change what side the bonds are on, right? But the skeletal structure has to stay the same. If N is the central, it's the least negative, and it has 1 attachment over here, 1 attachment over here, our resonance structure cannot be, because now we changed it. It needs to stay in this format, but you can move the double bonds. It's going to give you the same thing. And the reason, if you're asking why we did the double bond in the first place, was so this can complete its octet rule. Take a look, and then I'm going to go into something different. I'm going back to 505.
57 an hour, flying to Route 45. We did close 3 minus. Trying to find the difficult ones, but I feel like we're doing a good job. Okay.
I'll end this for today. So master this step first. Master getting the formal charges. Master making sure you complete the octic rule. And then I'm gonna expand upon that tomorrow. I'm gonna do another video just like this. Okay? And yeah. By the time you see this, it should be Friday. So good morning. But yeah. That's what we're gonna do tomorrow. We're gonna build upon it, but for today, what was the main takeaway? Where is the eraser? The main takeaway was one. The main takeaway was one. Choosing which element to start with, and that is the most electronegative, which is always up here as you go up and right. Now the least, and with the bigger atomic radius, is always going this way, which means just down and left. Okay, that's how we always choose which one is our central. Because as you saw, it mattered how we set up the oxygen for that NO2 minus. It mattered because we had to set up a certain way. That's why we need to know which is the central, because the central touches the other ones. Okay? Now what we also learned is formal charges. Because I'm about to wrap this up. Formal charge, which is electrons of element minus number of bonds minus these little dots minus the lone pairs or free electrons minus the free electrons, and then that gives us the formal charge of that specifically, and then once of that element specifically, and then once we add up all those formal charges, we get the formal charge of the entire element. So that's just the formal charge for one specific element, and then once we add up all of them, that's the formal charge for the compound. It's an element. That's the formal charge for the compound, adding up all of them. And we also learned resonance structures. Okay, I'll add something at the end. But resonance structures were also, oh yeah, what was it, N, O? You see how we went like this? To satisfy the octet rule, you know, this one had that. We just did it. Resonance structures just means you could flip it, but still have it mean the same thing. But if this was if this was, let's say this was, instead of NO2, it was NO chlorine or something like that. Weird. Then I'd be like that. O chlorine. Now it wouldn't matter which way it goes, because the formal charge could be different depending on what's happening. So just double check on that. But basically the resonance structure was what we know. And O2. Moving it to the other side because it would give you the same thing, the same element. So flipping it wouldn't matter, it wouldn't change the formal charges. It would just switch what side the formal charges are on. So this had 0, this had 1, -1. We flipped it. Sorry. This has -1, this has 0. We flipped it. Now this has 0, this has -1. It's the same thing. Resonance structures. That's what that was. And finally, I forgot this. Okay. So let's say we wanted to do lithium plus fluoride. Lithium, fluoride. Fluoride. How could we show this, right? So we know in like ionic compounds, it's like they're not sharing, it's taking it. So when this happens, we know lithium has 1 electron, right? 1 electron. Fluorine has fluorine has 7, right? So what we could do is Li plus, because it gained a proton, because the fluorine took its electron, and this just becomes fluorine. Oh. 1, 2, 3, 4. Now, if you look on your periodic table, what do these become when it loses a? When this gains an electron, it becomes a noble, which is what we were talking about, like filling up the octets. It's the same thing. But yeah, so we could write these ionic equations just like this because it took it, and now this has 8 electrons, and this has none, which is why it's Li plus and the fluorine is negative. So that's how we could write it. But yeah, that's a wrap. And yeah, that is it. I'll send another one tomorrow, or maybe later tonight, but probably tomorrow. And yeah, so just study making simple Lewis structures on ChatGPT. Study resonance structures and formal charges. Study that because tomorrow we're building on the Lewis structures and you're gonna need that. So build up on it, and then yeah. And there's a little more happening with chemistry, but don't worry about that right now. Just focus on Lewis structures, and then I'll see you tomorrow. Love you. Bye.